Electricity can be a tricky topic, but at its heart, there are a few mathematical relationships that can really help us to understand what is happening inside the circuits. So, in this lesson video, I'm going to touch very lightly on the theory, but leave most of that for other lesson videos, and we're going to go through those mathematical formulas. First up is current, since this is what we typically think of with electricity. Current is how fast the charge is moving, so it is defined as the rate of flow of charge. Current equals charge over time. I equals Q over T, or in units, amperes equals coulombs over seconds. This is what I call a defining equation. If you are asked to define current, you can just quote this equation, I equals Q over T. Make sure you explain what Q and T are though. We often think of current in terms of electrons moving around a circuit, but current is not the number of electrons per second, it's the charge carried by those electrons per second. One electron has a charge of minus 1.6 times 10 to the minus 19 coulombs, so if we have 1 electron per second going round a circuit, the current would be minus 1.6 times 10 to the minus 19 coulombs per second, which is minus 1.6 times 10 to the minus 19 amps. Current equals charge over time. Next, we have voltage, or potential difference. This one is more abstract, since the defining equation here is potential difference, PD, equals work done over charge, or energy over charge. In symbols, that's written as V equals W over Q. And in units, 1 volt is 1 joule divided by 1 coulomb. So, potential difference tells us how much energy the charge is carrying. More on that another time. For now, let's move on. In an electrical circuit, there are only 3 things we can measure easily. We can measure the current using an ammeter. Notice that an ammeter measures amps, but weirdly has no P in it. We can measure the potential difference using a voltmeter. And we can measure time using a stopwatch. And that's about it. So, what can we do with those measurements? Firstly, we could multiply them. So, voltage times current, V times I. That's going to give us V times I equals W over Q multiplied by Q over T. And the Q's cancel out, leaving us with V times I equals W over T. Work done per unit time is called power, so PD times current is equal to power. Building on that and rearranging things slightly, the energy transfer, called the work done, is equal to potential difference times current times time. W equals VIT. These two, P equals IV and W equals VIT, are what I call derived equations. If you are asked to define power, you can't define it using P equals IV. No, that's not the definition, so this equation is simply a very useful derived equation. What else can we do? We can divide, so let's try PD over current, V over I. And we find that for a normal resistor in a circuit, V over I is constant. It doesn't change. As you know, in physics, we like to give constants names, so this one we're going to call resistance. Yes, I know. You think of resistance as the thing that reduces the current in a circuit. Well, it is that, but it can also be calculated using the equation resistance equals potential difference divided by current. R equals V over I. Surprisingly, perhaps, this is the defining equation for resistance, the ratio of PD to current. Expanding on that, it's often remembered as V equals IR, which is fine, but V equals IR is a derived equation since the defining equation for PD was V equals W over Q, as I'm sure you remember from 2 minutes ago. There are two more equations, two useful derived equations, but no nice way to get to them. So let's just write them down to get everything in one place. These are resistor equations, and if we have two resistors in series in a circuit, the total resistance is the sum. So R total equals R1 plus R2. But if we put the resistors in parallel, the total resistance actually drops. So the formula is 1 over R total equals 1 over R1 plus 1 over R2. And that's it for equations for GCSE Physics Electricity. But I'm going to throw in a bonus one. The resistance of a wire depends on the length of the wire, the cross-sectional area of the wire, and the material. The resistance is proportional to the length, it is proportional to 1 over area, and it changes with material. So the derived equation is that R equals rho L over A. The resistance is equal to a constant that we call resistivity, that depends on the material and the temperature, multiplied by the length and divided by the cross-sectional area. You don't need that formula, but you do need to know how length and area affect resistance, so it's a handy way to remember if you like that sort of thing. That's quite a lot of equations, and you're not going to understand them at the moment. You're not meant to understand them at the moment, but having them out there, having you see them, will mean that as we approach them during the rest of the topic, you'll have some familiarity, and that's going to help us to understand electricity even better. As you go through, always remember to pay attention to these mathematical formulas, because they include definitions, and if you can define what current is, and if you can define what potential difference is correctly, then that's going to take you a long way in this topic, and it's going to help you to enjoy it as much as I do.